watching. So we're going to be doing this for about an hour tonight, and this is the Learn the Blockchain Solidity course. We are really just trying to get through this lesson 7. It's pretty much cursed at this point, so let's just jump into it.
Variables. Now, everything I'm about to go through is in the documentation, and there is a link to this, of course, in the GitHub repo associated with this course. Whenever we have one of these global variables, or these variables that stay permanently, they're stuck in something called storage. You can think of storage as a big giant array or a giant list of all the variables that we actually create. So when we say we have some contract called fundamental storage and we have a variable called favorite number, we're basically saying we want this favorite number variable to persist. Right? We saw in a lot of our examples, we had a favorite number variable that we could always call to see what this contract's favorite number was. Well, the way it persists is it gets stored in this place called storage. Now, storage works as this giant list associated with this contract, where every single variable and every single value in this storage section is slotted into a 32-byte long slot in this storage array. So for example, the number 25 in its bytes implementation is 0x00 with a ton of zeros, 19. This is the hex version of the uint256. This is why we do so much hex translation. This is the bytes implementation of a uint256. And each storage slot increments just like an array starting from 0. So for example, our next global variable or our next storage variable just gets slotted at the next slot that's available. So Booleans, for example, get transformed from their bool version to their hex. And we modified our sum bool variable to be true, and the hex addition of the true boolean is 0x000001. Every time you save an additional global variable, or more correctly, one of these storage variables, it takes up an additional storage slot. And what about variables that are dynamic in length, or that can change length? What about something that's dynamic? Well, for dynamic values like a dynamic array or a mapping, elements inside the array or inside the mapping are actually stored using some type of hashing function. And you can see those specific functions in the documentation. The object itself does take up a storage slot, but it's not going to be the entire array. For example, my array variable here at storage slot 2 doesn't have the entire array in storage slot 2. What it has actually is just the array length. The length of the array is stored at storage slot 2, but for example, if we do myArray.push 222, we do some hashing function, which again, you can see in the documentation what that is, and we'll store the number 222 at that location in storage. The hex of 222 is 0x0000DE. So it gets stored in this crazy spot, and this is good, this is intentional, because 32 bytes may not be nearly big enough to store my array if our array gets massive. And it wouldn't make sense for it to put the elements inside the array at subsequent numbers because, again, the size of the array can change and you're never going to be sure how many subsequents that you need. So for my array, it does have a storage slot for the length. For mappings, it does have a storage spot as well, similar to array, but it's just blank. But it's blank intentionally so that Solidity knows, okay, there is a mapping here, and it needs a storage slot for its hashing function to work correctly. Now, interestingly, constant variables and immutable variables do not take up spots in storage. The reason for this is because constant variables are actually part of the contract's bytecode itself, which sounds a little bit weird, but you can imagine what Solidity does is anytime it sees constant variable's name, is it just automatically swaps it out with whatever number it actually is. So you can kind of think of not in storage is just a pointer to 123, and it doesn't take up a storage slot. Well, when we have variables inside of a function, those variables only exist for the duration of the function. They don't stay inside the contract. They don't persist. They're not permanent. So variables inside these functions like new var and other var do not get added to storage. They get added in their own memory data structure, which gets deleted after the function has finished running. Now, you might be asking, okay, well, why do we need this memory keyword, especially when it comes to strings? We saw before that we had to say string memory. The reason we need it for strings is because strings are technically this dynamically sized array. And we need to tell Solidity, hey, we're going to do this on the storage location, or we're going to do it in the memory location where we can just wipe it. Arrays and mappings can take up a lot more space, so Solidity just wants to make sure, okay, where are we working with this? Is it storage? Is it memory? You have to tell me. I need to know if I need to allocate space for it in our storage data structure. And again, everything here you can read in the Solidity documentation. Now, in the GitHub repo associated with this course, if you go to contracts, we've actually got an example contract section called Fun with Storage, where you can play with and look at a lot of this stuff. And we even wrote a little script called Deploy Storage Fun, where it'll print out the storage location of some of the different variables. Feel free to give it a run if you want to try. I challenge anybody to write some functions that define the storage slots of the elements of the arrays and the mappings, and then find the data inside of those as well. We use a function here called getStorageAt, which allows us to get the storage at any one of these slots. And this is to reinforce that even if you have a function as private or internal, anybody can still read it. Anybody can read anything off the blockchain, and you can test it exactly with this. If you go ahead and git clone that or copy paste the code yourself, you can then run yarn hard deploy --tags storage, and you'll run the deploy script for that storage, and you'll see printing out the location of storage in each storage slot with a fun contract that we made as an example. Now you might of course be asking, okay, Patrick, why are you telling me all this? We're just trying to get this gas price down. Why are you telling me all about this storage thing? Well, the reason I'm telling you all about this storage thing, anytime you read or you write to and from storage, you spend a ton of gas. Remember how I said when we compile our code, we compile it down to some crazy weird bytecode? Well, let me show you on Remix what this looks like. We can go to compilation details. We can go to bytecode, and we see this weird hex object, 0 blah, blah, blah. But we also see these things called opcodes. Now, this bytecode here represents these opcodes. Each one of these opcodes represents a small piece of everything in this bytecode. And in fact, in our hard hat, we can go to artifacts, build info, and we can see these opcodes in the build info. We can do a command F or a control F for opcodes, and we can see opcodes for different contracts. These opcodes represent what the machine code is doing, and they represent how much computational work it takes to actually run our code and do stuff with our code. The way that gas is actually calculated is by these opcodes. There are a couple lists here, but here's one that I'm going to use, this EVM opcodes. And again, there's a link to this in the GitHub repo associated with this lesson. Well, if we scroll down, we can see exactly how much it costs for each one of these opcodes. So for example, anytime we add, it costs 3 gas. Anytime we multiply, that's 5 gas. Subtracting, 3 gas. We have all of these opcodes that cost different amounts of gas. And in our functions, here's kind of a sample contract. If we're doing adding, anytime we add, it's going to cost 3 gas. Anytime we save to memory, it's going to cost gas from some other opcodes. These opcodes combined show us how much gas we actually use. Now, let's look at a lot of these opcodes and how much they cost. 3, 5, 10, 3, 3. Balance is 700. So getting the balance is a ton of gas. Let's keep going. Getting the size of an account's code is a lot of gas. Copying an account's code into memory. But oh my goodness, what is this? Save word to storage costs a ton of gas. That is 20,000 gas. And sload, load word from storage, costs 800 gas. These are 2 of the most important opcodes, sload and store, which stand for storage load and storage store. Anytime one of these opcodes fires, we're spending 800 or 20,000. There's a big asterisk there because that can change a lot. But we're spending a ton of gas anytime we work with storage. As developers, anytime we work with some stuff in storage, we want to go, boy, this is about to cost me a lot of gas. And a best convention for making sure we know that we're working with a storage variable and we're about to spend a lot of gas is to append an S underscore right before them, which stands for storage, right? So we're saying address to amount funded is going to be a storage variable. Funders is going to be a storage variable. Owner is not going to be a storage variable. It's immutable. A best practice for immutable variables is prefixing it with an I underscore. Constant values are also not in storage. So for constant values, we want to keep them caps locked like that. Aggregator v3 interface, public price speed. Yep, you know it. That is going to be a storage variable. So we want to append an S underscore with it. So we're going to do a little bit more refactor. We've appended these appropriately to update everything. So instead of owner, it's going to be I underscore owner. And as a developer, we'll read this and we'll go, this is going to be much cheaper than a regular variable. Okay, that's great. I'm going to work with this I underscore owner for my modifier. Awesome. Is owner anywhere else in here? Okay, right in the constructor. I owner underscore owner is message.sender. Price feed is a storage variable. We should, as developers, we should see the S underscore when reading this and go, okay, we're spending a lot of gas to store this. Perfect. Okay, great. Let's keep going. Great, we've updated all the owners. Okay, well, what about address to amount funded? In VS Code, if you do Command F or Control F and you hit this little down arrow, you can actually find and replace all of these address to amount funded with S underscore address to amount funded. Hit it like that. And since I updated one, I got to backspace that one now. So now these are all updated. Let's do the same thing with S funders. Let's update everywhere it has funders just to be S funders. and we probably doubled up here. Yep, let's undo that. We already updated all the I owners, so now let's update all the price feeds. So let's look for price feed. We'll update it with S price feed, and then we probably doubled up right here, so we'll undo that. Okay, great. Now that we've updated everything in here, we can scroll down and we can, oh, whoops, so I doubled up there too, sorry. We can read through our code and go, okay, where are we reading and writing to storage way more often?
How is it I was awake when I first started this, but now I need a nap? Ugh. You saw me reach for the pillow and was like, "What are you doing, Amy?" But okay. So every time we use stuff that's in storage, it is taking up a lot of memory, or it's expensive. I was using multiple screens. No, I'm not using multiple screens. And now are you going to let me? What are we doing? Okay.
Then we probably need to. And that's when we get to this withdraw function, which seems rather suspect to reading and writing to storage a lot. So let's take a look at what we're doing here. Okay, so first of all, I can see that when we're doing a for loop here. And every time we do a for loop, we're just constantly looping through all of this code. Every single time, we're doing a little compare option here. We're saying, okay, is our funder index less than sfunders.length? Sfunders.length. This means the longer our funders array is, the more times we're going to be reading from storage. That's incredibly expensive. Where else are we calling this? Oh my goodness. We're reading from storage a lot and saving it to this memory variable and then updating our storage variable with it. Wow, so we're reading from storage a ton here and we're reading from storage a ton here. Okay, then we have to reset our funders array. There's really no way around it. And that's pretty much it for our reading and writing to storage. We could probably create a withdraw function that's a lot cheaper. So let's go ahead and create a function called cheaper withdraw. Function cheaper withdraw.
Okay. Okay. So that's a thing that hasn't happened yet. So, but that's probably a good thing. So we do function cheaper with public only owner. Okay.
That's going to take what we've just learned and make a cheaper withdraw that's much more gas efficient. So we'll keep this public payable and have it be only owner. We're not going to change anything there. But what can we do for at least this part here?
With withdrawal.
Here, we don't want to keep reading from storage here, and we don't want to always have to keep reading from storage here. We're like doubling up the amount of storage we're reading from. So instead, what we can do, we can read this entire array into memory one time, and then read from memory instead of constantly reading from storage. And that's going to make our lives a lot cheaper. So we can create an address array memory funders.
So yeah, this makes sense. Address, memory,
equals S underscore funders.
I think this is S underscore.
And now it's going to start making sense why, for arrays and strings in our functions, it makes us say, hey, is this memory? Is this storage? What is this? And we're telling it we want it to be memory because memory is going to be a lot cheaper. So now that we're saving it into our funders, oh, and a quick note, mappings can't be in memory. Sorry, they're just too weird and too wacky, so Solidity just doesn't let you do that right now. But now that we've saved our storage variable into a memory variable, we can read and write from this memory variable much, much cheaper, and then update storage when we're all done. So what we're going to do now is we're going to say for UN256 funder index equals 0, and we're going to base.
Okay, I think we're actually going to do the for loop because I think that was the issue with the test. This last test. So function cheaper withdrawal. Okay, so funders equals S funders, and then for uint index equals 0.
Basically rewrite everything, but just using this memory array instead. We're going to say funder index is less than funders.length instead of sfunders.length. And then we're going to say fund.
so funder index less than funder's length, except it's not s underscore, it's just funders. And then
funder index plus plus. And then in here, we're going to do
so for
do nearly exactly the same thing, except we're going to say address funder equals funders using our memory array and not s funders.
So this is a plural funders. And inside the for loop, we're doing address funder singular equals funders funder index.
Of funder index. And then we're going to say S address to amount funded funder.
So funder equals funders funder index address to amount funded. This is, I think it's literally just
equals 0. So we're resetting our our funders mapping here. We're using our memory variables instead. Then we're going to do the same thing. s_funders equals new address array of 0. And then
this is just resetting everything to 0. And then
we're going to do the same thing. Bool success, comma, equals.
okay. So
sowner.call value address this balance, and we're going to send it nothing. And then acquire.
I looked up here. We'll just put this in here.
Success. Like that, actually. Oops, sorry, iowner, not sowner. Now that we have this function that we think is cheaper, let's go back. Back to our test, and let's run this same multi-test here, but with our cheaper function. So I know this could be a little bit tricky to copy paste, but let's copy this entire massive test. Let's come down here, paste it, and we'll change the name saying cheaper withdraw testing ... And
Okay. I'm fighting consciousness more than I am learning anything right now. What did we paste? This whole what thing are we? So this. Did Command C?
test here, but with our cheaper function. So I know this could be a little bit tricky to copy paste, but let's copy this.
Seems to me that they want me to basically do this whole thing. Okay, question though. It's like a describe situation. Is it inside this before all? I'm a little confused.
Entire massive test. Let's come down here, paste it, and we'll change the name saying cheap.
Okay. What's going on? What all did we paste? Okay. This is only frustrating because I am tired. So. So close to being done with this section. So close. So we have it allows us to withdraw multiple funders. Only allowed owner to withdraw. Where's cheaper? What was I working on? What the heck? I am really confused. Also, if I do hard hat test, this is gonna fail super hard, right? I should have committed this. The issue here is the fact that this is not inside of a transaction. Or like, let's try hard hat test. And this is unexpected because I did so line 67 according to that. Okay, I'm gonna take a quick nap and then we're gonna figure this out.